So, when we want to pose this as an optimization problem, recall when I was talking about the example problem, I told you specifically that we can help the carpenter by choosing a design which leads to minimum amount of material that goes into fabricating the tray. Because if you fabricate the tray with minimum material, you are going to minimize the overall cost that is needed to fabricate that tray, and that will help the carpenter. So the goal that we have, at least with respect to the problem, which we did not have in the previous mathematical formulation, was to minimize the material volume. So what we want to do is we want to minimize, and this is our overall goal or objective. And in order for us to formulate any optimization problem, we typically need to have a given objective. One of the other things that I want to make an assumption that, if you looked into the video, the thickness of the plywood was very, very thin, right? So that's an assumption we will make, that the thickness T is also fixed, and it is very, very small compared to the other dimensions of the tray like length, width, and height. So we will assume that this tray, the width, the thickness of this tray is very, very small. Now, if you made that assumption, and if we say that our goal or objective is to minimize the material volume, then what we should be doing? First of all, we should be doing that how can we use this information to formulate a mathematical optimization problem, and that's what we are going to focus, okay? So remember that our goal is to minimize the material volume, and how we can find out the material volume that goes into making this tray. So if you look into this tray, I just showed in the video that the carpenter was using 5 different pieces, right? So he basically used, this piece right here, 1, then he had this piece which was 2, right, and then this piece which is 3, then the side piece which is 4, and this bottom piece which is 5. So he was fabricating these 5 pieces, okay? So, and then, he essentially cut them, and then he was trying to assemble them. So if we take, the area of these pieces and multiply that by thickness, that will give me the material that goes into making this tray, and add them up, then it essentially helps us in calculating the overall volume, okay? And recall, how to compute this. If I want to compute the area of this first one, then I can multiply the height by the width, and that gives me the area of the first plate, and that multiplied by the thickness is going to give me the volume of the first one. And remember, for 1 and 3 is very similar, so we can take 2 of this. Similarly, we can take length and height, multiply them together, that will give me the area of this piece, and same thing will be the area of the piece number 4, okay? And if you multiply that by thicknesses, that will give me the volume of material that goes into making tray part 2 and part 5. And then we take the bottom piece, which is length, into width, which gives me the area of this, rectangle, and that multiplied by small thickness gives me the material that goes into making part 5, or the base part of it. And then I can add them up, and that will give me the overall material volume that goes into making this tray itself. So let's see how we can use this information, and then how we can write. So what we want to do is we have to define our goal or objective, and as I illustrated in the previous slide, that we can compute the overall volume of material, okay? So this is not the volume of the tray, this is volume of the material that it goes into making the tray itself. It's function of 3 variables, W, L, and H. We know this H is, constant, is given fixed, right? And as I showed that I can compute the overall area by taking the area of 1 and 2, 3 and 4, and 2 of them are symmetric, so I can use that equation, and I can, use this overall formulation, and I can write the overall. So you can see this WL is essentially related to the 5th part, right? The length into height were the 2nd and 4th, whereas 2WH was 1st and 3rd. So that's how combined together I wrote this overall equation. So this will be the overall equation that captures how much material is needed to fabricate the tray itself. And our objective is essentially to minimize this overall material. So we want to minimize that needs to go. So this is an equation that describes that I want to minimize this, okay? And this is something that I'm interested in minimizing, okay? So that's the goal, and that is typically in optimization is known as the objective function, Okay, so this, when we write something, a goal as an equation, then the equation or the function that describes the objective or the goal is known as objective function. Okay, so that's one concept in optimization, that the equation that describes the goal or optimal sense is the objective function. Okay. Now on top of that, right, what information we have? We have other information which we already used in the hyperbola example, right? And that information is also there. We need to have a tray that has to hold a specific volume V, and the height of the tray is also fixed, right? So this objective function, where we are interested in minimizing the material, is also subjected to or constrained with the other two pieces of information, which that the tray has to have a capital volume V and the height of tray is fixed at 2 equal to h. So when we write this, right, where are other things, this while solving the optimization or while focusing on arriving at the optimal solution, we have other things that we have to respect is termed as the constraint. So that's the other information, and the couple of other constraints are there, where the length has to be greater than or equal to and width has to be greater than or equal to 0. Why? Because this dimensions cannot be negative for a physical entity, and so that's why you have to respect a solution, or you have to get a solutions where the length is at least positive. It cannot be negative for a physical object. So all of this criteria which are describing what this design needs to satisfy is termed as constraints or constraint function in optimization. Okay, so the goal function is this, but this goal function has to respect this other information that we have with respect to this problem, and those functions which needs to be respected by the goal function or objective function are known as constraint functions in optimization. So that's another important concept, that typically an optimization problem might have objective function and it might have constraint. In some cases, you might have objective problems where there are no constraints and there are no other set of equations that you need to respect, and you might fall into a category that you have only objective function, and that will be known as sort of unconstrained problem. Whereas where you have constraint function, those class of problems would be known as constrained optimization problem. Okay. So what are the design variables in this? As you know, that capital H is fixed, H, right? So the only two things that we can play with is the width and the length of this variable, and those are the two design variables that we can play with, and we need to find out the optimum value, or W star or L star, what I indicated, which will be minimizing the material to fabricate the tray while respecting the set of constant, is what we are looking in our overall framework. Okay. So before I go ahead and try to solve this using an analytical approach, one of the other important things that I want to quickly cover is there is a standardized way of writing optimization problem. Okay, so we have written this optimization problem. There's an objective function. We have this equation, set of equation. In that setting, the standardized way, which I'll show you quickly, what you do is you rewrite your constraint in such a way that you are you have written a specific way that could be used to feed it to computer.